All right, so again, what I was saying, the rate of this reaction, listen up, the rate of this reaction must be constant. So in order to keep this number constant, you always need to divide the change in concentration over time or multiply it by a fraction, whatever makes sense to you, by the coefficient. All right? So I use this example over here, and I sent it in the picture because if C and D are forming twice and 3 times as fast as A and B are being depleted, then you have to divide this rate by 2, divide this rate by 3, so that the rate of the consumption of A is equal to the rate of formation of C. So in other words, relating to this, the reason this is the expression is you have to take in the coefficient, the stoichiometry. You have to take that into account when you talk about the rate. All right, so I know I keep kind of saying the same things over and over. I'm trying to say it a little differently, but really you're trying to keep that rate number the same. And if it's the same for all of these, but yet they form at different speeds, then you have to divide them by the coefficient to take into account that different speed of formation or consumption, depending on what it is. So that's how you write an expression, like in general. Okay. The next question. Was this multiple parts?
The top one's A, the bottom one's B.
Oh, there we go. Okay. All right. So if they give you actual reactions, your reactant concentrations are going to be negative, and your product's going to be positive. So it's the negative change of H2 over change in time, negative change in I2 over change in time, but positive change of HI over time divided by a half, divided by 2, multiplied by a half, because there's a 2 in front of it. For every 1 mole of these that are consumed, 2 moles of this are forming at the exact same time. So if this is forming twice as fast, then we need to divide it by 2 to keep the rate the same for all 3. So you're going to see questions, we're going to do it in our notes. Calculate the rate with respect to HI. Calculate the rate with respect to H2, and if you're given numbers, it's a lot easier and it makes more sense because you're going to get an actual value. You just have to divide this one by 2 because there's twice as many of it. Twice as many moles of it is a better way to say it. So I hope I'm being clear. Feel free to interrupt me and ask questions. All right, this one is dividing by 5 because there's a 5 in front of the BR. This one, there's no coefficient, so there's nothing there. This is a 6, and that's a third because there is a 6 and a 3 in front of it. So, am I missing the products here? Oh, so here's a reactant. This is the product?
Yeah, there's H2.
Oh, water, right. So water isn't involved in the rate expression. No, that because the reaction is carried out in aqueous phase, we do not monitor the concentration of water. This is really important for equilibrium, the next unit. When you dissolve something in water, or if there's a reaction involved in the water is really just the solvent used to separate ions so they can react. The water doesn't really play a role in the reaction. Does that make sense? Mm-hmm. You're just using it as the medium to do the reaction in. Plus, there's so many moles of water, right? Let's say you have like 0.5 moles of these things, or you're going to have like 100 moles of water, right? If you have like 0.1 grams of something dissolved in 500 milliliters of water, there's so much water, it's kind of, you can ignore it. The water isn't really affecting anything as far as the reactions are concerned. So that's important to try and lock that in there, and remember when we get to equilibrium, we write what's called equilibrium expressions, and water is never in an equilibrium expression. It's just the medium for the reaction. So we only use the reactants and products. Hopefully that makes sense. Next question. This is different. This is not aqueous. This is not. What is this question? What is this reaction showing? It's the formation of water, isn't it? Yeah. That's totally different than doing a reaction in aqueous solution. You're forming water from its elements. Does that make sense? Okay, so this is going to be negative because it's depleting, negative depleting, and this is going to be positive, and this gets repetitive. Now I hope everybody's with me. I hope you got it now at this point. you just take your coefficient and divide the rate by that coefficient. The way we write it is multiplied by half, just because it looks cleaner. If you were going to write change in H2 over change in time, parentheses over 2, it just doesn't look, I don't know, it doesn't look as good. This is just a cleaner way to write it. And just to refresh your memory, the brackets mean concentration. So the brackets actually stand for the word concentration. So instead of writing H2 moles per liter or capital M for molarity, we just put it in brackets. That means moles per liter. All right, and then here's B, negative 1/4, negative 1/5 for that, positive 1/4, positive 1/6 for that. So the point of this was, one, learn how to write these, and two, repetition to get good at it. So if you were really confused, obviously you didn't get a whole lot of practice, but hopefully now you got it. Hopefully now it's making sense. We're going to do a practice problem in our notes right after this. So that's 6, 7. Oh, did you have to calculate that?
Yeah.
Okay, did they give you numbers? Obviously they must have.
Yeah.
Okay, so, all right, suppose particular moment, I forgot I gave this one, reacting at a rate of 0.066. So that 0.066 molarity per second, that is the rate. That is the rate. At what rate is NO2 being formed? Okay, so the NO here, let's see, okay. So the rate of NO's formation is 0.066. It's negative for the NO. So if they're telling us that the nitrogen monoxide is being consumed at a rate of 0.006 moles per liter per second, then at what rate is NO2 being formed? What's the coefficient? What's the ratio between NO and NO2? 1 to 1. So if this one's being consumed at this rate, then NO2 would be formed at the exact same rate. The answer is 0.066 moles molarity per second. This is just like what we're going to do in our notes, except I make you calculate a change. In other words, I don't give you a 1-to-1 ratio. So let's just kind of talk about that. So let's say there was a 1 in front of this, NO, and a 2 in front of the NO2. What would you have to do to that number? So if there's a 1 in front of NO, and that's the rate. So let's say this is just that, and that's 1/2. So if this was a 1 to 2 ratio, what would you do to that number to calculate that rate? Divide by 2. That's what this shows us. That's the whole point I'm trying to make here, is if you start getting numbers, which you will, we're going to do practice problems, if you know the rate of one of these things, you can calculate the rate of the other by just plugging it in the rate expression. You just have to use the ratio correctly. So if this was a 1 to 2, then you would have to divide that by 2. Okay. Well, because it's 1 to 1, it's the exact same. We're going to do a problem in our notes right. What's going on? Is this?
That's part B of it.
Oh.
Same question, part B.
Okay. Oh, here we go. Sometimes I just get a little overzealous. I like talking about, stuff like this. I know that sounds crazy. But this is exactly what I was just talking about. I should have kept reading. So if they give you this rate of 0.066, but it's a 2 to 1 ratio, then you have to cut this rate in half, and that equals oxygens. That's why you have to multiply NO's rate by 0.5 in order to equal the rate of O2. So to keep these two numbers the same, you would have to divide this one by 2. That way they both would equal 0.033. That's what I keep trying to explain, and I hope I keep saying it enough, it's making sense to you guys, that this rate must be cut in half if you want to keep it the same as the rate of oxygen, because there's 2 for every 1. So that's why it's 0.033 molarity per second. And again, it's negative because it's being consumed. It's a reactant. So I'm going to say it one more time. If you have twice as many NO being consumed at the same time as half as much of O2, then you have to divide that rate by 2 to get oxygen. All right, and then the last one. Here we go. This is more like what we're doing in our notes here in a minute. All right, so suppose at a particular moment in the reaction, molecular hydrogen is reacting at a rate of 0.074 molarity per second. At what rate is ammonia being formed? All right, so the rate expression is right here. All right, so they're telling us that the rate of, what is it? Hydrogen is 0.04. So the rate of this is 0.04 molarity per second. At what rate is ammonia being formed? So essentially, what you're doing here is, forget this is even here, and forget this, because these are all equal. You're putting 0.04 in for this entire expression. So it's 0.04 equals 1/2 times the change in concentration of NH3 over the change in time. So that's essentially how you're going to solve for the rate of NH3. So, anybody have an answer?
0.049.
0.049. Let's find out. There it is. There it is. So what they did here is they did 2/3 because they set it equal to each other, right? So they just took the two parts that they needed. This is the ammonia rate expression. This is the hydrogen rate expression, all right? And you can just plug in the rate expression here for the H2. That's essentially what they did, but they combined the fractions there, okay? And when they did that, essentially they're just taking this and taking the inverse, right? So essentially, maybe I can make this a little easier. They're getting rid of this half, so they're multiplying it by 2, that's going away, multiply this by 2. So it's 2/3 times this rate equals this, right? So if you get rid of the half, now this is what you're solving for. This is the rate. That's what the question's asking. You know this is 0.074, so 0.074 times 2/3 is 0.049. That's a good AP question. Okay, that's what they would ask on an AP test. All right. And you know what? Don't be surprised if it's a multiple choice. Except instead of 0.074, they'll give you a number you could do without a calculator. And this might be, a half. So then it's just 0.5 times a number. You can do that in your head. So. Obviously, we're going to do a little bit more practice with this. But again, you set the two equal to each other, and then you're solving for the one the question's asking for, and then you plug in what they give you. Just have to use the stoichiometry to figure that out. Okay. So B is the exact same process. So let's see. Do we all have answers for B, or were we too confused?
Answer.
Well, we're going to do notes anyway. I was going to say I'll give you a minute to do this on your own right now. But, all right, so this time we're setting up the equation with the N2 equal to H2. This one's a little easier because there isn't a fraction we have to get rid of here. You're just solving for this rate right here. Because rate is defined by change in concentration over change in time. So you plug in your 0.074 right here, and all I do is multiply it by 0.3333, or a third, either way, however you want to type it in, and you get negative 0.025 molarity per seconds. You can set up a proportion too. Some of you, I know Skylar, you like doing proportions. You can do a proportion, that'll work too. You just have to make sure you set it up correctly. So this would be a third of this. Hopefully that's making more sense. Okay, is that it, Homer? All right, lights please. Let's take some notes. I'm going to give you a practice problem right now, just like this. All right. So we're done writing rate expressions. That was the homework was supposed to help you with that. Here we go. So we're going to do the decomposition of hydrogen peroxide. What is that equation? Decomposition of hydrogen peroxide. There we go.
H2O.
Plus O2. You need 2 of these and 2 of those. Yep. Okay. At a particular point in this reaction, H2O2 is decomposing at a rate of 6.0 times 10 to the negative fifth molarity per seconds. At what rate is O2 being formed? And you got to show some kind of work. Don't just do it in your head or do it on the calculator and then that's it. So show work. Now, if you've been paying attention, trying to learn this here, you should know, all right, it's a 2-to-1 ratio, so obviously it's not the same, right? The answer is not going to be the same. H2O forms at the same rate H2O2 decomposes because it's 2-to-2. Oxygen won't because it's a 2-to-1. So not only do I want you to get an answer, but I want you to make sense of it. Does it decompose? I mean, does it form faster or slower? So once you have your answer, circle it, put a box around it. I'm going to come around and check, see what you got. And this may be easy for some of you, I don't know. Well, I want to see. Write your rate expression of just what you need. Write the rate expression of H2O2 and set it equal to the rate expression of O2. Do you want me to write that on the board with you? Or do you want to try?
No. Am I doing the rate expression of the whole thing?
Nope, forget H2O, we don't need it. Do you want me to do it with you or let you go?
No, I got
Alright. Okay, so you got the rate expression. So now I gave you a rate. So you plug that in for the one that I gave you. So you plug that in for the change in concentration of H2O2 over change in time. So where you wrote change in concentration of H2O over change in time, you plug that number in, 6.0 times 10 to the negative fifth.
the entire thing.
Just the part that is, don't get rid of the fraction.
The change in time gets rid of those two.
Yep, so the change in concentration over change in time is that number. Because that's what M over S stands for.
And then is that how you just solve for?
Yep. You solve for the change in concentration of O2 over change in time. Once you get it, like once you can look at this and it makes sense, it's much easier. I know that sounds like a silly thing to say, but it's one of those things where you won't forget. It just starts to make sense once you get it. Sometimes I know it's hard to get to that point. Some of you, a lot of you got it right, but some of you are getting a number I'm not sure where you're getting it from. Yep, maybe I'm not thinking clearly here. So here's the rate expression. 1/2 times the change in concentration of H2O2 over the change in time equals the change in concentration of O2 over the change in time. So now we're going to wait for Skylar here to give us the answer. But what we're doing is we're taking this number and we're putting it right here. We're taking this out and plugging that number in. So it's 1/2 times 6.0 times 10 to the negative fifth equals this entire thing here is like my x. That is the rate of formation. Rate is defined by change in concentration over change in time. That is what rate is equal to. So that's what we're looking for. So all we do is multiply this number by 1/2. So what's that, Skylar?
Answer?
Yeah,
Times 10 to the negative fifth.
right. That's it. Some of you got 1 point something. What'd you do? Did you multiply it by 2?
Yeah.
Okay.
What is it like a negative? The like
If
negative.
it's a reactant. Because reactants are losing concentration. So if you were to do it, delta means final minus initial. So if you were going to measure the final concentration minus the initial, just make up any number. Let's say the initial number of moles is 10, and then the final number is 0. 0 minus 10 is negative 10.
So how come the H2O2 is a negative?
See,
It
that's
is.
thing, why don't you plug in a negative at the,
You can. This can be a negative number, that's fine. But this number has to be positive, so I just didn't put it in there. Yes, you're right. That should be -6 times 10 to the negative 5. You're right. I left it out. I'm just going quick, I guess. But that negative can't be here because this is a positive change. It's gaining concentration, not losing. Kind of like endo is positive, exo negative, same thing. It's just a symbol to represent decreasing or increasing. The number actually, the value isn't actually negative. You can't have a negative concentration. It's just showing it's decreasing in concentration. Let's try another one. We need to get to a different thing here today. So one more example. All right. All right. So we have 4NH3 plus 5O2 yields 4NO and 6H2O. Now I just wrote this down. I'm gonna have to make it up as I go here. Actually, wait a second. Yeah, I'll just make it up. All right. If the rate of formation of NO is 2.0 times 10 to the negative third molarity per second. Calculate the rate of decomposition of O2. And I have to do this really quick myself. Let's see here. And again, see if the number makes sense to you. Like in the last problem, the rate of the formation of, what was I asking for? O2, that rate is smaller than the rate of H2O2, which makes sense. If O2 is losing twice as much at the same speed as O2 is forming, it's definitely going to have a faster or increased rate. So the bigger this number, the bigger the rate, means the faster it's reacting or being consumed. Hey.
It's gonna be,
How are you feeling about that?
because we're solving for something on the right side. When you're solving for something on the right side, yes, it's gonna be negative. It has to be positive, it's gain is positive.
Just take negatives and negatives on top.
Yes,
But
you're gonna solve for a negative.
just solve for the number and then worry about the negatives in terms of like what's losing. So
Yeah, if it's on the left side, it's gonna be negative.
instead of like taking negatives from the actual equation, just do it based on what's given.
Yes.
Yeah, Michaela, I think, emailed the AP environmental teacher at Gilbert today. So I'm gonna talk to Michaela today
That's why I tried asking.
and see if I can, or I'll just email her and ask her, can you give me a ballpark of how much you spent when you first started the class? You know, it's 5,000 or 2,000 or what are we talking about? You know, so. But she did help me, she gave me some stuff, so. Because I'm basically done, except for that. I just don't know how much.
I'm pretty excited about that class. I like this.
Yeah, I mean, I'm gonna have to buy stuff. Like, I don't have boots to wear in the field
No.
or all that. Like,
That's true.
We're gonna have to,
That's
you
true.
know, so, I mean, I have like snow boots and work boots, but it's
I think
different
it
than,
hurts it.
you know, so, it's gonna be
Okay,
cool.
we shouldn't do that.
It's good too, because then you can kind of like teach all that to your daughter too.
Oh, yeah,
So
no, it's awesome.
good.
So,
It's awesome.
it just hurts. I'd rather-
Alright, thanks. Okay, 0.0025, right?
I know.
2.5 times 10 to the negative 3. Here's how we do it. So 1/4 times the change in concentration of NO over change in time equals negative 1/5 change in concentration of O2 over change in time. So there's our rate expression. All right, this is given to us as 2 times 10 to the negative 3. So you can either get rid of the fraction and bring it over here, or multiply this by 1/4. Doesn't matter. I just multiplied it by 1/4, and then I divided by 1/5, and that gave me this rate, which is the answer, and that is 2.5 times 10 to the negative 3, which makes sense because if 5 of these are decomposing for every 4 of these, that rate makes sense. All right? So in other words, this rate here must be higher. This must be decomposing faster than this is forming because more of it is decomposing at the same time as less of it's forming. So that number is slightly bigger than that. And in the last example, it makes sense again because by a factor of 2, the oxygen is being formed in half the time of the H2O2 decomposing because it's a 2-to-1 ratio. Okay. Skylar, you feel better?
Yeah, I got it.
And everybody else good? Good. So we're done with that. All right, last thing. Rate laws. Last thing today. This is just the beginning of rate laws. Rate laws are a big deal. Your books are still open, right? If not, go to chapter 13. Go to page must be, yeah, page 573. So rate laws. So we just went through the first section on that chapter there. Now we're in the second section. This is like one of the units that the book is very useful for. So anyways, if you look at the top, it says rate law expresses the relationship of the rate of a reaction to the rate constant and the concentrations of the reactants raised to some powers. That makes no sense until we get to an example. So let's just first get the general example from the book. It's the same thing I have in my notes. If I give you a reaction A, B, B, yields C, C, and D, D. So little d, little c, little a, little b, that's your coefficient. A rate law looks like this. K is the rate constant, and that's a lowercase k. Bless you. Lowercase k, that might look like capital there. Lowercase, it's called the rate constant. And the rate constant does have a unit, but it depends on the type of reaction. So I'm going to hold off on the unit for a minute here. And then, just like in the book, you have the concentration of A, which is one reactant, raised to X, raised to some power, which will make more sense hopefully in a couple minutes. And then B, raised to Y, it's going to be another exponent. Now, X and Y could be the same exponent, or it could be different. It depends. Now, the good news with this is whenever there's rate law questions, they have to give you numbers. They have to give you charts. So like if you look at the bottom there of 573, they have to give you the concentration of F2 and ClO2 and then the rates. So in other words, to solve for these rate laws, which I'm going to explain what it means and what's going on, you need to have information. All of this is done experimentally in real life. These rate constants are determined experimentally in real life. It isn't anything you're expected to just know. So what are we going to try and get done in the next couple minutes is figure out what the heck this shows us and how to solve for a rate constant. So if we look at the example there, because I'll just get right to the example. Well, actually, no, sorry. Let me back up. We should talk about reaction order. If you look at the shaded rate law, rate equals K, this thing here. Underneath it, I'm just going to read that to you. X and Y are numbers that must be determined experimentally, like I just told you. Note that in general, X and Y are not equal to the stoichiometric coefficient. That's really important. I mean, if you want to write it down because it helps you remember, write it down, but you need to know, you need to memorize that. That the coefficients, so little a, little b, for example, are not the exponents. Now, you may think, why are you telling me that? Well, later, especially in equilibrium, you're going to see how that gets confusing. So you just need to remember that. The earlier you can memorize it, the better. Your coefficients are determined, the exponents are determined experimentally, and that's from numbers in a chart. So they're not the coefficients. Let's see. When you know the values of x, y, and k, we can use equation 13.1 to calculate the rate of a reaction as long as you have the concentrations. X and y specify the relationship between the concentrations of reactants A and B and the reaction rate. Added together, they give us the overall reaction order. Let's write that in our notes. Reaction order, it's the sum of the powers to which all reactant concentrations appearing in the rate law are raised. Reaction order is kind of a big deal. There's like different classes of reactions. Some are first order, some are second order, some are third order. We're going to learn about those. And it really all doesn't start to make sense until you kind of learn a little bit more and see the charts and see how to use this. So if you're really confused, just bear with me. Obviously, you have to pick up with this on Monday. Okay, so let's use this example here. Now, I don't know if I have a different example in my notes. I do. Yeah, I'm just going to use the one in my notes because I have everything figured out already. If we look at, let's just write this one, the one from the book. Let's put it in our notes. The only thing I want to do here is practice with you how to write a rate law. So if this is the equation that you're given, so write this down, please. Oh, that's a 2. If I was to say write the rate law, this is what we would do. The concentration of products are never in a rate law. It's only the concentration of reactants. So you would write rate equals K. K is a constant. And again, I'll show you Monday how to figure that out. The concentration of F2 raised to some power times the concentration of ClO2 raised to some power. That 2 in front of it is not playing a role yet. So, if you're given an equation, a thing called a rate law is what we will write for them, and this is how you do it. This is a constant. Again, we'll learn more Monday about it. All you do is take your reactants, put them in brackets, and raise them to some exponent. How do you figure out the exponent? Look at the bottom of that page. You got to do some math with the concentrations and the initial rate to figure out the exponents. All right, and we'll get into that. Flip the page. I want you to just, because I'm running out of time, look at 575. Forget all that mumbo jumbo on 574. That looks a lot more confusing than it is. Go to 575. I just want to show you another example of how to write the rate law. If you look at that example, it's 2NO plus 2H2 yields N2 plus 2H2O. Skip down where it says strategy, and then you see the rate law. Rate equals K times NO in brackets, because that's a reactant, raised to X, H2 in brackets, raised to Y, again, because that's a reactant. So the basic thing to learn here today, before we get out of here, is if you're given a reaction, can you at least just write one of these? The general formula for a rate law. Monday, we're going to learn how to calculate this, and that. But, if you look at this example, on 575, you see the chart, experiment 1, 2, 3. That always is provided. You're always given a chart, and I'll show you how to use the chart to get those numbers. All right? So I'm going to have to stop because the bell's going to ring. I think I should give you your problem set today.
What is it? Do we have like before homework?
Say it again.
Do we have before homework?
My plan